I'm Pavitra. I work as a developer advocate at OnSite. I'll be your primary instructor today. And I have with me Kim. She's my co-presenter. Kim is a software engineer at OnSite as well. So she's my colleague. She's going to be here to help with any questions y'all have. So this is a tutorial, and this is a hands-on tutorial. So we're going to get started with setting up your hands-on experience. So in the chat, which is the session chat, I'll share a link to the setup instructions, which we can walk through together there. Where do I see all the attendees? Oh, people in this session. We have a lot of people. I see now. Okay. Hi, everyone. This is interesting. All right, so if you go to that link that I've shared in the chat, you will hop onto this Google Doc. Yeah, I see a lot of folks are here. So how many people do we have actually? Like, do we have a clear number? Can't tell. So we have about 50, 50 instances allocated. So if you go to the very first spreadsheet, like it's the first point here, and open it up, yeah. So if you put your name against one of these instances, you can just take that username, and we have 50 allocated right now. So if this is full, I think Kim can also drop in the chat if folks aren't able to log in at some point. If this is full, you can still follow along, but you may not be able to just do this hands-on because all of the tutorial materials are designed to work on we're going to work with really large data sets on like a cluster of machines, which not everyone will have access to. Okay, so I'm going to let folks do this quickly. And while you do that, I'll just walk you through how to sign up, right? So yeah, go in, just add your name against one of these usernames and make sure to just keep this tab open so that you have a reference. And then you can log on, you can navigate to training.quantsite.dev. There is a link in the doc that is open. Oh, I already have it open, but you will see a login window with sign in to Keycloak. And there you can use like PyData, your number, right, that you selected, and the default password, which is given here in the doc. I'll actually just increase the font. Yeah, that should be more visible to everyone. Okay, so once you sign in, you'll be prompted to change your username, sorry, your password. So just remember the the password that you set, because you will need that password once during this tutorial. Like you may need it for like signing into the dashboard, which we'll look at in a bit. Okay, so just keep your password on hand. But once you hop in, you will see a Start My Server button. And you'll see like Nibari, that's when you know your sign-in authentication process is complete. Click on Start My Server and select the medium instance. You're gonna need, like small is gonna be very slow for this tutorial, so we need medium. All right, click on medium and hit start. After that, actually, you know what? Tell me in the chat, I guess, once you've started your instance, and then we'll get the tutorial materials cloned in this instance. And also, if you have any questions, and I went by a little fast, so if something isn't clear, just please ask us. This is the most important step, right? Like this is, once you have the tutorials, then it's going to be smooth sailing because we have a clear flow there. Okay, how many people have? Yeah, we have a few folks. Yeah. All right. So the next step, like once you're in the instance and you started your like medium instance, you'll be in a Jupyter Lab window. So folks are familiar with Jupyter Lab, this should be like pretty much what you know. There you can open your terminal. So the terminal, for folks who are not aware, will be in the last section in the launcher. The launcher should be open at the moment you like are dropped into the instance, right? If not, if the launcher isn't open, let me just close this one. And yeah, if the launcher isn't open, if you can just click the plus button here, or you should be able to get the launcher from File, New Launcher as well. And the terminal is available in under Other. Open the terminal and write git clone the repo. So
Pavitra, did you say the password?
yeah, I didn't say it out loud, I think, but it's available here. It's Nibari, capital N, Nibari _ capital U user, exclamation 321, and the @ symbol.
So that's the password, and then the usernames are what is shown in the Excel spreadsheet. So
Yeah.
the usernames are PyData _1, _2, and all you're doing is claiming a username because we only have so many usernames available. So we have 50 usernames available. So what you're doing here is you're just going to claim a username by writing your name or something in the your name line or your name column, and then you'll log on to the Nibari instance using that username and then the password from the Google Doc.
Great. Yeah, thanks for clarifying. Yeah, always. Maybe just let us know once you all have like signed in, so we can move on. Okay, thank you, Melissa. Yeah, we were at cloning, right? So yeah, the moment you clone, the repo should be available in the sidebar, in the file navigator here. You can open it and go to introduction or intro to task and like follow along with us as we walk through these one by one. Okay. I think that's about it. Like if in case you like close the browser tab or something, you can just go back to training.quantsite.dev and log in with the same username and password that you set, right? And all the material, like even the work you do should be in a saved state there. Okay, I think folks have, yeah, got up. Okay, now we can then get started with the tutorial. I'll do like another just extended intro, I guess, and let more folks do the setup. So the platform we're using is Nibari. Both Kim and I are Nibari maintainers. I think, yeah, core team members. And this tutorial, just make sure the environment that we have, or the kernel, if you're familiar with Jupyter Lab, we'll be using the global PyData global. This is just the way Nibari handles environments. This environment is in the global namespace. If you're interested in environments, there is another talk tomorrow, which I'm presenting about packaging and environment magic that goes on behind the scenes. But we won't be going to environments today. Just make sure in case this is not set, it should be default selected for you. In case if it's not, you can select this environment and everything should be good to go. Okay. That's the main bit. And there are some exercises. The environment name, that's Kim. Okay. Thank you. Yeah. There are some exercises here. We'll stop for the exercises, or we may continue based on like timing and yeah, how fast or slow we go today. All right, so with all of the setup done, we can jump into the task. So this is before we even get into this, like in this tutorial, our main goal is to just give a very practical, like very getting that intuition right view of big data analysis, right? And we are going to focus mainly on like tabular data. So not so much NumPy, but more Panda style. And the two main libraries that we'll use here are Task and HVplot. These are the libraries we are super familiar with, but we are generally thinking about just how to work with big data in a parallel distributed manner. So we hope most of the intuitions can carry over to any other framework you use as well. but we'll be focusing on these two libraries in particular. Okay, so let's start with, actually, yeah, also this is, initially the first version of this tutorial was a 4-hour tutorial. So we have condensed this down, and like, because we've presented that a couple of times, we realized, we can condense it down to a way and like make this even more digestible, right? So a good preliminary thing is, before we start with any big data analysis, it's useful to work with a subset of the data set. It's just easier to work with. You can work with, you can use your local computers, like any machine you have to work with it, and just anything you want to do, like exploration, setting up your workflows, all of this can be done in like, with the subset itself. And after we have, you're unable to log in. Maybe Kim, can you help Brian? Yeah, thank you. Like once we have a workflow set up, like you understand the data set, you know what you want to do, then we can think about the next step and like working with the entire full data set. So we will be skipping over the subset or like the single machine part and jumping directly to big data workflows. And for this tutorial, we are going to be using the airline on-time performance data. So this is a data set, like the data is published by the US Department of Transportation. And we have just downloaded it and put it up in Parquet format on Google Cloud. The instance is also hosted on Google Cloud. So all of this is happening on the cloud. This data set is about 70 gigs on disk. So this is really a big data set, which that's why we say you probably won't be able to work with this locally, like if you want to just follow along. Okay, so starting with need for scale, we won't be executing this section, but you can if you want to. Your kernel will crash, so you may just have to restart your kernel and start over. But why do we need to work with these new tools, Dask, HVplot, Nebari? It's because you cannot work with large data sets beyond a certain size with the traditional tools that we love, which is NumPy, Pandas, Matplotlib. All of these are designed to be serial tools, right, in the PyData ecosystem. And they work with data set loaded into the RAM, or like usually we just say memory, and there's only so much memory we have. So what we can do instead is work with data that fits in memory in small chunks, and then combine the results and have the analyses over the entire data set. Okay, so that's why we need scale to make sense of the large, and make use of the large data sets we have right now. So with that, let's start with the first library we look at, which is Dask. Are folks familiar with Dask? Like just to get a sense of room? Or have you all done any kind of parallel distributed work before? Use Dask one project. Awesome. Yeah, basics of Dask. I've used Fast Spark extensively. Nice. Okay. All right. So, okay. Did my audio just cut out, Kim?
No, you're good.
I think it did.
It's a little crackly still, but
I don't hear you. I think I'll have
to
join back.
Oh, no.
Would you mind just continuing for a little bit, and I can take over.
Okay. All right. So while Pavitra is figuring out her audio, so her audio, it was a little crackly on and off. We tried 1,001 different things before this, before we got started, and this is as good as we can get it. So please be patient with us, or be patient with the audio issues. Although I don't know why it entirely went out. Hopefully she can resolve that. Yeah, so I wasn't prepared to present. So a little bit about Dask. So Dask is a Python package that is used for parallel and distributed computing in Python. The idea behind Dask is it gives us an API that is familiar. So it has several layers of APIs. And the one that we're going to talk about first, and I think used primarily today, is the data frame API. So if you're familiar with pandas, this is going to feel, actually, I believe it's identical to the pandas API. The DAS data frame API is the same. Oh, so we're not the only ones with audio issues. Good. So what DAS does is it allows us to do parallel computing. So rather than setting up a network of parallel computing and having to manage the parallelism on our own and distribute the work amongst different computers, DAS handles all of that for us behind the scenes. So all we have to do is transform our data calls into DAS data frame API calls, and then it will distribute to the parallel network we have behind the scenes on its own. All right, Pavitra, are we good?
I hope so. But
okay,
yeah,
great.
It's nice to know we're not the only ones
yes.
facing this. Yeah. So yeah, as Kim said, like the whole point of Dask is, yeah, you don't have to learn a whole new API, but like use the Pandas API you know fairly well, and Dask will handle everything else. And not just parallel computing, but also distributing the workload, which is my favorite part about Dask. You can use it on your local machine, you can use it on a cloud instance or on HPC, but it's still the same API. Everything else is handled behind the scenes pretty seamlessly for the most part. Okay, so intro to the data frame API. Also, like Dask also has an API that mirrors the NumPy API, which is called the Dask Array, right? So for all your array workloads, you can use that. And Dask Array is also extended into, like, I think Xarray uses Dask as well, if you really want to do big data geospatial work. But yeah, we'll be focusing on the data frame API and Pandas workloads. So let's start by doing an import. So as you would import Pandas as PD, usually we do DD for Dask data frame, and read CSV, again, very familiar. And right now we are starting with only 4 months of data, just to illustrate a couple of points, and then we'll move to the full data set. Okay, so this is just grabbing September, October, November, December of 2020. So these are actually only 4 months. It's not 4 months across several years. It's only 4 months of 2020. And let's look at what DDF actually holds. So this is where lazy evaluation will come in, but that actually hasn't done any computation yet. It has just grabbed some metadata. Like, it knows what this data frame looks like, all the column names. It knows how many rows of data this has, and like what the data type it expects these to be, right? But actually, nothing has happened yet. But we look at lazy evaluation in just a little bit. And but before we do that, there is a caveat with Dask, which is, yeah. So we see a head, which is, again, one of the first things you would do with Pandas, fails with a data type mismatch. So I said Dask is, it's kind of, I think it's reading like one row or something and trying to infer what data type the entire column is, which is not always accurate. And whenever there is a clash, there will be an error, because it's trying to read the entire column, assuming the data type, compared to something like Pandas, which is going to read the entire column and then input the data type. So, but that's a luxury that Dask does not have, because it just can't read your entire data set at once, right? So one of the first things to think about, or like be careful with, is being explicit about the type of data you're using in a big data scenario. So to just make sure we get this right, we've already created a dtypes.json file with the correct data types. So I'm going to import that and provide that as an argument here. And then that should not have any problem reading our data set and actually getting those first 5 head values, and also all of the columns. So now we've actually learned how to load the data in correctly. Now coming to lazy evaluation that I hinted on earlier. The whole, I guess, how task, this is one of the preliminary aspects of task, which is all of your computations are set up once and then executed at the end, hopefully. That's what we mean by lazy. It's being lazy in evaluating your workflows. So anything we want to do here, so I'm going to do a count operation. So task has created a logic for performing this operation, but it hasn't actually done the work yet. In fact, the work it has set up can be visualized with the visualized command. And this is the work it has set up. It needs to read the data first, which it hasn't done yet. Then it will do a count operation, and it will aggregate all of these and give you a result. And everything in the same horizontal layer will be executed in parallel. Okay, and this is what we call a task graph in task. So every time we discuss, like, task graph is one of the key terminologies we use in the task land. So visualize is showing you the task graph, and task sets up a task graph, right? And then it computes a task graph. So task graph is like the intermediate state to enable lazy evaluation. Okay, what is 1 to 6? These are the 6 chunks. Good question. Do I have it here? Yes. So DAS data frame is working in partitions, and here we see 1, 0, 1, 2, 3, 4, 5, 6. These are the, that's 2, 4. We have 7. Yeah, so we have 7 partitions, which I think should have been visible even up here. We have n partitions equals 7. So these are the 7 actually pandas data frames that task is going to evaluate this on and then aggregate the result, because it can work on these pandas data frames in memory, and it'll do all of these in parallel and then aggregate the results. Does that make sense, Anton? Okay, so to actually do the computation, we need to use the dot compute, and then we will actually get the result instead of this structure. And to elaborate this again, a DAS data frame at its core is just a bunch of pandas data frames partitioned. Like each partition is a pandas data frame. And almost any compute workflow that we set up is going to be worked on in these individual pandas data frames and then combined at the end in various ways that Dask handles behind the scenes. And yeah, there we have the actual result. There's a small note here, which is certain functions will do an implicit compute. So here we called a compute to get the result, right? This is where the actual work happens. Task will decide the size number of partitions for us. Yes, it will. It will by default, but you can also set it. No, I did not. So that's also a good question. So it will infer this in a logical way, depending on how your data is stored and wherever you're storing it. Like there are some formats that actually you can store partitions separately. But yeah, DAS does do this automatically. You can use a repartition command to change partitions as you need to. Okay. And to actually see the number of partitions at any point, you can use the end partitions. All right. So is this clear so far, like how Dask works? Some data types like Parquet allow you to partition on saving. Yeah. Right. And I guess also how it decides on that is based on a certain, like till a certain size, right? It can hold in one partition. So that's how each partition is decided. But I might be wrong. I'll verify that. Okay. So moving on. Also, like in this particular tutorial, we are using Parquet. So we actually have partitions saved in the data format itself. So so far we've talked about Dask, and as I said, Dask works both for general parallelism. So you can use what we've done so far, right? Like we haven't done anything distributed per se. All of this is just parallel computing, and this will work on your laptop. So it will, even if the data is stored on your laptop or on the cloud, it will bring in each partition will be brought into memory, worked on, and then aggregated. So far things should work on your local machine. And to move to a cloud or like an actually distributed structure, we bring in the concept of clusters, right? And in any distributed cluster, we have a scheduler and we'll have a few workers. So a scheduler, the workers are the ones that actually will do the work. Like when you do .compute, they're the ones who are going to do the computation. The scheduler thinks about and orchestrates the work and like passes on correct workflows to like parts of computations to each worker and like gathers the results and like manages all the workers, right? And in Task, we have a client. So our client right now is the Jupyter Lab interface. And the client is the interface between, like for us, like Dask and the Dask cluster. So client is how, or a Python script, wherever you're using Dask, they are the client is what we interact with directly as users. Is that clear? Okay. So Dask has a concept of local cluster, which we will not be getting into. But if you do want to use Dask locally, you can, emulate a distributed computation on a local machine using Dask's local cluster. Because I think also the recommended way to use Dask or a local machine. Okay. And to use Dask on a cloud system or an HPC system, we have certain other like our sister projects in the Dask ecosystem. So we'll be using Dask Gateway. So Dask Gateway is a library, part of the Dask project, right? Like not the Dask core library, but the Dask project as a whole. So this lets us use Dask in a containerized manner, and like Dask Gateway is powerful. You can use it on cloud systems, but I think also HPC systems. But like there are a lot of options if you want to deploy it yourself. Nibari uses Dask Gateway by default, so all of our workflows with Dask are going to use Gateway as well. Everything okay so far? Yeah, awesome. I can't tell who is doing the thumbs up, but it's really appreciated. So now in the notebook, we're making calculations on a local machine. No, we were doing it so far, yes. Like till right before all the computations we did so far were being done only on the medium instance that you started on the cloud. Everything was happening locally there. But now we will move on to a cluster. Okay, so to use a gateway cluster, we will import gateway, create a gateway instance, and set some options. Let's look at what these options are. So here we see an environment and a cluster profile. So these are options that we've made visible through Nibari, but there are a lot more options that Gateway directly exposes. But for us, we just need to make sure you have the right environment and the right cluster profile. So this means like every worker that is created, right, like all of the other machines that your work is going to be distributed on to like leverage all the resources that the other machines will have. So your medium instance has how much? We have 16 gigs of RAM. So that's the amount of data we can work with. But now when we start 5 more instances with 16 gigs of RAM, we're going to use all of these resources together. What is fs.glob? Let's just come back to that, Brian, maybe at the end, right? I think that's just to make sure we have the correct path together. I'm not sure. Maybe we missed the import, but maybe Kim can take a look and answer you. Okay, so all of our, and the environment is important because all of our workers also need to have the right set of libraries to work with, right? So all of them need to have the same, like they need to have Dask data frame, and the right versions of Dask data frame to work with. So this is what these two options ensure. All right, so after selecting those, we will actually create a cluster with these options. let's start it. We should get another handy widget. Okay, so here we see manual and adaptive scaling. So let's pause here and discuss what these are. In manual scaling, you can set the exact number of workers you want to use for your task, which works in most cases, right? If you know that so many workers are going to be enough, and like you have a sense of that, all good. But sometimes you don't, and that's where adaptive scaling is really useful, where you can set a minimum and maximum number. So and number of workers will be created if there is need for them. And this will be handled by a gateway behind the scenes. So for this tutorial, we'll start with 5 because yeah, we've tested this. We need at least 5, and we will do a maximum of 10. So and we'll actually be able to see as new workers are spun up. So and click on adapt. In the real world scenario, you will actually do like 1 to 10 because you don't want to have resources idling, because all of these workers are on the cloud. They cost actual money to keep up and running. So you only want to use them as and when you need it. For this tutorial, just to make sure you actually have these and don't have to wait for new resources to be allocated, we'll work with 5 minimum. Okay, I've hit adapt, and I'm going to connect a client to it. So client is, I'm connecting my Jupyter lab to our cluster. Okay. So far, so good. I hope there's no stalling here. Sometimes, like when we've had a lot of folks access task on Nibari, we've seen some slowdowns, but give it a few minutes. Like if you still don't see something, just let us know in the chat and we'll look into it. Okay. Okay, now comes this is my favorite part about task, which is the dashboard. So you see a dashboard link here, right? For the first time you use this is a Nibari specific thing where you need to log in to make sure you can access the dashboard. So go ahead and click this. This is opening the UI for me, but you may see another like sign in option. Like when you log into Nibari for the first time, you saw a Keycloak sign in. You may see that. So just use your username, which is PyData underscore whichever number you chose, and the password you selected. Once you do that, you should have this dashboard open. And this should be a one-time thing. We don't need to continue doing that. Okay. So just make sure this works. But this is one way to access the dashboard, right, in a new browser window. But we can also access it within Jupyter Lab. So the 1, 2, 3, 4th icon in the leftmost sidebar is, what is Nibari? Awesome question. I will get to that in just a bit. Let's complete the task section, and then we'll answer that. Okay, we're also already 30 minutes in, so I'll speed up a little bit. This is the Dask Jupyter Lab extension. It took mine some minutes to new cluster. Yeah, that's what I was hoping. Yeah, okay. And click on this magnifying glass icon. So this is going to grab the dashboard link from your active Jupyter Lab window and populate a list of plots. So these are diagnostic plots. So why are these actually important, and why is this so powerful? In a distributed setup, when your work is happening on several machines, it's really tricky to keep track of what is going on, right? If it was on your local machine, you can look at like activity monitor, like on a Mac, or like equivalent ones on other machines, and see what's happening. But when you have like work running on 10 or 100 different machines, you need it's very hard to make sense of logs even at that scale. So you need a different way to understand what's going on, and that's what these graphs provide. So these are plots about your computation. Okay. So we're going to open a few cool ones. Let's open the cluster map. This is in alphabetical order, just if you are having trouble finding things. So cluster map, progress, and then task stream. And let's open the worker's memory. Where is it? This one. Because this is Jupyter Lab, you can also move these around and fit them on your screen in a way you like. go task stream here. I need progress on the side and workers memory. Okay, does everyone have the plot set up? Let's work through these plots one by one. So the cluster map is showing us visualization of the scheduler in between in purple, and all of our workers are around it in this yellow, ochre, orange color. And right now, if you remember, we did minimum 5 workers and maximum 10 because we requested 5 workers minimum. We have 5 workers here. And as your workflows, you missed what to do in the dashboard. Okay, just 1 second, Ross, I'll get back to you. So as more workers are requested, you will see them show up here. Okay. I've got the orange dots, or the workers. I've got no orange dots. That means there is just you may need to wait a little bit, Irina, to start getting workers. But that's why we requested 5 minimum. You'll slowly get the first 5 workers. Okay, so how do you open the dashboard again? So first off, click on the dashboard link to make sure you're actually logged in. Right, so click on the in the client widget that we have. This is in the manual versus adaptive and Dask gateway cluster section. If you click on that, you should get an option to sign in just for the first time. Sign in with your username and password to just access the dashboard on Nibari. And then click on the Dask icon in the very left sidebar here. It's the 4th icon from the top. You should be able to click the magnifying glass icon, which will grab the link for you. And then just click on one of these tiles to open the corresponding plot. And the plots you need is listed in here itself. Yeah. I don't see the icons on the left. You may not need to log in. Like that's this is, yeah, I'm not sure. Maybe you only log in the first time and it's a little flaky. Sometimes you need to, sometimes it grabs your authentication information. I open the dashboard and the link and it's empty. Yeah, it will be, you may not see, oh, interesting. You may need to click enter after the link is populated. Yeah, that may also be the case. So the link here is basically the same link as your as the link displayed here for the dashboard.
And after if you paste that link into the Jupyter Lab widget on the left there at the top, you have to press enter or it won't populate those orange tiles.
Mm-hmm. Yeah, if it's not connected, maybe you need to log in, is my guess. And if you don't see any workers, it's because the workers haven't been allocated to you, just wait a little bit. You should get workers. Had to paste the URL. Okay, yeah, that's the other option. All right, so let's move on, and I'll just let us know in the chat if more folks have issues. That was a cluster map, and the rest we'll discuss these, as we do computations then. Okay. So let's start with basic computation. Let's not do this as an exercise, but just do it together. So we are calculating the longest flight distance in our data set. And because we have a dot compute, the actual workflow is computing, and like only when it computes will you see activity in the diagnostic plots. Okay. And yeah, we'll discuss the plots as we do more computations. And yeah, maybe you saw there was another worker created and then removed because it wasn't needed. Okay, let's end this intro to Dask section with a disclaimer. Just always remember to close your cluster, right? These are, as I said, actual machines taking up actual money and resources. So if you don't shut these down, and if they are not handled in a different way in your system, like, yeah, you're going to incur a lot of costs. So for Dask, you can shut down the cluster with cluster.shutdown. And an additional optional step is also to do a client.close, the connection from your Jupyter Lab interface to the cluster. You're closing that. Okay, so that's the intro section complete. Any questions so far? Is that clear? Yeah, awesome. We had a question about what is Nibari. So Nibari is a data science platform. Under the hood, it is a opinionated Jupyter Hub distribution. Do folks know what Jupyter Hub is? Here, if it's the first time you're hearing about it, Jupyter Hub is a Jupyter project. Is a part of the Jupyter project ecosystem, of the Jupyter ecosystem, and designed to allow more folks to use Jupyter notebooks collaboratively. So it provides ways to have shared compute and shared environments. And what Nibari does is it gives you a quick way to deploy your own Jupyter Hub with like same defaults, right? So it has Dask built in, it has environment management built in. So that's what Nibari is. And we have used Nibari to set up this platform for you. Yeah. Thank you, Kim. If you have any questions, we can also discuss that at the very end of the tutorial. Okay. The graphs will be empty for two reasons. Like either you don't have workers and the compute is actually not happening. And it's going to be empty like until we do an actual computation like with .compute. Okay. If there are no other major questions, let's move on to more task computations. So I would suggest most folks here shut down and try to restart your cluster. I am going to continue with the same cluster just because I'm presenting and I don't want to wait for more resources. Okay. So now we are in number 2. You can access this through the file navigation panel here. Okay.
Pavitra, you want to go over how you get the panes on the right?
You mean setting these up? Oh yeah. So you can just click on the name here or like the tab heading. Yeah.
I think if you could go over clicking on the Dask Jupyter Lab extension button.
Mm-hmm.
Yeah.
Let's open a new one. Let's go with.
So we get those by clicking on those orange buttons.
Yeah, these should open automatically in your active window, and then you can arrange it as you want. The cluster map has only one circle. It's because you haven't been allocated workers yet from GCP. All right. So we used a manual approach, right, to create your cluster. You can also do it programmatically using this code section, which I let you all run. I'm going to connect to an already running cluster with these lines of codes, which you'll also do in the next notebook. So this is not something you're missing out on. Oh, I have to import task though. And let's do this. I'm going to just, yeah. All right, so I'm connected to the same cluster, and let me also get back a client. Awesome. So this client object is what, as I said, like lets us connect to the cluster, and like although you don't see it being used directly, like when you do a dask.compute, right? Like the client object is being used to connect to the cluster. Okay, so let's again read back our data set. This time, let's read the full data set, not just 4 months. And I did mention briefly that some functions like head do an implicit compute, like behind the scenes, and that's why you saw some activity happening here. So, okay, getting back to the tutorial and like just the practical aspect of the tutorial, we won't go through like a step-by-step intro to Dask and how to work with it, right? We're gonna look at just the things you need to be aware of while working with task. And this notebook is structured in like a, let's talk about the best practices and cover task like in that way. So the first thing is shuffling. What we mean by shuffling, let's actually see it with an example. Oh no, my image is not visible. Okay, let's let this run. I will take an opportunity to explain the plots while this runs actually. This is going to take at least about 5 minutes to complete. So our data, if it is not, there are some computations, like for instance, when you do a sort, right? Or if you do like setting the index, which needs a sort, or any other function, like which, if you need to think of it like, think of an average versus how would you calculate an average versus calculating a median in a distributed system where you're only working with like chunks of data. Average, you can do like average of each and then like sum of each and then do an average together. But like for median, you will need to sort this entire data set, which is actually present as small partitions, and then take the middle value, right? So one is a lot more different than the other, and like a median operation will involve a lot of like data transfer between partitions, right? So that is what we mean by shuffling. Shuffling is anywhere you need this data transfer between partitions, and like a lot of it is required. And in a distributed setup, we kind of want to minimize shuffling because data transfer is the most expensive thing you will do in a distributed workflow. So in this section, in fact, the first or our default data set, the full data set we downloaded here, is not sorted. And you'll see it takes forever to complete. And once the plot loads, the plot will look really, really wonky. So the best practice here is generally when you work with big data sets, try to do a sort once, right? Before you even start your actual workflow. You want to make sure you store the sorted data set and you're working on that from the beginning. So that's what we do here. Starting this cell and moving on for the rest of the tutorial, we'll be using a sorted data set. Yeah, I will let this complete. It'll take a little bit. And here, let's do like a aside and talk about the plots again while the computation runs. Okay, so let's go to the task stream now. So this is literally what is being executed on the cluster being visualized in a single plot. Back, let's look at it a little closely. So each of these, just if you hover on them, these are all bokeh plots, they're all interactive plots. You can hover on them to see what was being executed. And I believe all of these are like the total number of threads, right, on all the machines. So each thread is like one horizontal line. And the green is like successful, good compute, and red is all the data transfer. So the more red you have, the less efficient your distributed compute is. So progress is like, so the task stream is like a worker-based view or like a thread-based view of what's going on. Progress is like what is actually happening. So this task, which has almost 1251 subtasks, right, is progressing slowly. So all of these will happen in the distributed. You should see these all of the colors are connected. So in the task stream, you'll have series group by, I can't see the whole, yeah, or like yellow is series group by count combined. So that will be the same thing in the task stream as well. So you're seeing the task based view here and how it's progressing. The more red I see, the more skew. I don't know what you mean by skew, Nishan. I would say there's just a lot more data transfer happening. That's also what you see as red lines here, like in the cluster map, like the red dotted lines are also like inter-worker communication. Yeah. So as these tasks progress, so do the task streams. And workers memory is fairly I mean, it's as the name suggests, it's how much memory is being used per worker. Right now we have 10 workers, and you see all of them here. Right. I will actually let this task complete. The first one, I will stop the next one, but y'all can have it by. All right, I see we're also at like almost 50 minutes. So how about we also take a like 2-3 minute break? I drink some water and let this computation complete. Let's do that. I'm here to answer any questions though, like if you have, but I want to continue with the tutorial section. You can also go grab some water if you want. And we'll start back in like a couple of minutes, oh, time zones. Oh, no. So in about 2 to 4 minutes, okay? Any questions though? And also like, have folks caught up? Have you received workers? Well, I hope so. Your group by count cell is running. Awesome. Did you sort the data set by float date? Flight? Yeah, I believe that's the one. Is that it though? Let me just check I kind of don't remember. Yeah, we started this way back when. I would think so. Yes. I'm not sure though. I will. How about I take a look at the very end, right? Let me. Like if you have questions, if you have time, I can then answer you, or I'll let you know on Discord. Like I'll just look. I need to look up the scripts and see what we sorted it by. Like it is definitely date. I don't know if we like combine the like year, quarter, month, or if we use the float date. But it's definitely sorted by like overall date though. There's also some it's going pretty fast on my end, but I can see the stream is a little slow. So there is also like I'm screen sharing and it's getting to you. That's also why this may look a little slower. It should be much faster on your on your own instance. Sorting mechanism. Yep. Made a note. Or maybe Kim, if you can look up, I think there's a script in our in the complete tutorial. Where we can see how we sorted this. All right, so let's just gradually jump back into the tutorial. I hope this complete soon enough. All right, let me give myself more space here. So this is the unsorted data set, and you can see the plot is all over because it's not in the correct order. That's also why we had like almost over 1,000 tasks. In the sorted data set, because we don't have to do the sort again, we have much fewer items. And like once the plot shows up, you'll also see it's like, that's the plot you expect when you do a group by count. Okay. Let's start discussing the next couple of concepts as this computation completes. So persisting. So persisting is the CKM, the overall progress is just the combination of all progress bars. Yeah, that's correct. Yeah, across all workers. Yeah. Okay, a single bar for all progress. There, yeah, I don't think there is one in the in our diagnostic plots though. Sorry, got distracted by the chat. Coming back to persistent data sets and intermediate values. So here, so far, what we've done is we have data on the cloud. So all of our data is actually stored on Google Cloud, right? We are doing some compute here. And Dask, this is a compute I want to execute. Dask does like creates the logic. We do that compute. Dask then goes in and tries to execute this, also like by reading the data, performing the compute, and then giving us the final result in our local client. Now, this works fine. Sometimes just to speed things up, like if you want to use the same data or like the same intermediate values for multiple executions, right? And if you're actually thinking of doing a compute so many times, it's going to take a while. So what you can do instead is persist data, your certain like intermediate work or a portion of your data set. So what persist does is it's going to store that in the or like on the workers itself. So I think we will do a persist right after this computes, and you'll see the like that the workers have some memory reserved, and you'll see a certain amount of we will see it in the graph itself, and like it's very clear that this is being persisted on the workers and not being read in each time. Okay, so this will make things a little faster because your data doesn't need to be fetched and pushed to the workers each time, but it's already there. And this also helps with data locality. Okay, it is like data locality is a combined, or like it's a part of persisting in a way where Dask will try to assign work or like assign tasks. Like the scheduler tries to assign tasks to workers based on the kind of data it has locally. So that's handled by Dask behind the scenes. That's what data locality means. So that way that your data, the data doesn't need to move between workers, and we like reduce overall like the data transfer costs here. All right, just waiting for this task to complete. So this is why this is taking so long. I'll actually give that a bit of a side note here, because we are plotting the data set, and we'll discuss the tree plot in the next notebook, where we'll actually use this on a much smaller data set and not the full complete data set, because plotting requires an additional set of computations. It's not just doing the compute and plotting it directly. So that's why this takes so long on the complete data set. But the actual, only if you don't plot and do just the computation, the 5 to 10 workers that we've assigned should be enough. The next computes will be pretty fast, okay, compared to this one. All right. So this is it's over, and this plot looks a lot like what you would expect from a group by count. Okay, now let's move on and do the faster and fun bits. So to want to understand like persisting, we will do, actually, let's open up another plot, which is the graph. Where's the graph? This one. Yeah. So this is the distributed task graph, right, in the diagnostic plots. So right now there is nothing here. The scheduler isn't doing anything. We haven't set up anything to be computed. So that's why this is empty. But when we do persist something, we'll see stuff there. That's why I want to start, that's why I want to have it here. We are going to compute the number of departure and arrival delays per day. So we are doing two different things, departure and looking at two different columns in our data set, departure and arrival, but we are grouping them both by flight date first. So there is like a little bit of a part of this operation is same for both of these different computes. Let's do these one by one and see how long it takes. So this is the task graph. Work has been queued, right? We got more workers and they've started computing this. Once these complete, we will persist a portion of our data set. So also to remember here is we don't want to persist the entire data set because our workers will then run out of memory. Like you don't want to be persisting 70 GB. Like we don't have that much, like actually RAM or working space. Now this task here. Just 1 second, I'll get Christopher. So we don't have that much space, so we want to persist the data we'll be using here. So here we are using departure delay, arrival delay, and flight date. These are the three columns, and we'll persist only those three columns once the first part of this completes. Now to your question, just the graphics sold me. I can look at this already. I know. As I said, this is my favorite part of task as well. Are folks like able to follow along? Like I get the same part, a little behind, a little ahead. Is this pace okay? Too slow, too fast? I see the 800R. I think we should make time fairly well. Is everything clear? Like just let me know if there are any issues like hearing me, understanding me, all of that. Okay, I see 2 thumbs up. Wait for a couple more, just that I know that y'all have all caught up to where I'm at, and then we can continue. Our first compute is done. So our departure delay is done. Now we're doing arrival delay. This took about 1 minute 50 seconds. So I'm also like screen sharing. Yep, to the graph. Should the graph on the second data set be slow? What do we mean by the second data set? Sorry, the sorted data set. I didn't read it correctly. Sorry. It should be faster. Like when you plot this, when you plot like the HP plot on the second one, the sorted one, it should be faster. Is the number of tasks equal to number of partitions? No. So tasks are the total. So we have a set of operations that need to happen on each data frame, right? Like, so let's do a very simple like average, or like, actually let's do a sum. The very basic operation we could do, like, and so what we'll do is do sum in each partition, right? Palo, we'll do it and then we'll add all of the sums and then provide the result. So if we had 5 partitions, so our initial sum, we'll have 5 tasks. Then doing like adding all of these together is another one. So we'll have in total 6. So like depending on the complexity of your workflow, number of tasks is going to differ. But like, of course, the more partitions you have, the more tasks you will have. But it's not a direct relation. Does that make sense? That's true. Thanks, Kim. Number of workers will affect the speed at which our compute happens. Okay, we have times. Both of these took about like over 1 minute 30 seconds. Now we will persist a portion of our data. And the important thing to note here is when you do a compute, you get the final result, right? Like when I did a compute here, I got the final result, like with the answers, like, and sometimes in the compute, you got like a single number, right? This is the final answer. What a persist operation is going to give back the reference, right? So here we are persisting a data frame, so we are getting the same structure of a data frame to work with. That's an important like caveat when you persist things. Now let's do the same compute again. I did, okay, yeah, that was a lot quicker. And you can see here, all of the subset of our data is stored in memory. And like there's some, even though there's no compute happening, there's some extra memory being used on certain workers. And our task graph also shows that there is memory being used. Okay, so that's what persisting is. And I did say you can use intermediate results. So if we don't have it here, but we can do like a client.compute and have like two different things within it, like A comma B. So if A and B are two different like computations, they can share certain internal. If there is like a shared section of the task graph, like the set of executions, certain results can be shared between them to make it faster as well. But you can learn more about that in the Dask documentation. We aren't covering that today. Okay, so the next like best practice around this. So first we looked at reducing shuffling. Second, we looked at persisting when necessary and only persisting what is necessary, right? Third is partitions. So the number of partitions you have is important. This gets really important in array workloads, right? Because usually you have really large arrays and the way you chunk just plays a tremendous role in the performance you get. So in the data frame land, we call these partitions. In array land, these will be called chunks usually. So if you have too many partitions, like if you have like 1,000 partitions and only and like way too many workers or whatever, like your scheduler becomes really bottlenecked, right? Because it's now having to the number of tasks will increase based on number of partitions, as I said, not linearly, but like obviously like more partitions you have, the more tasks you have. So our scheduler is like becoming really overworked. So we want to avoid that just for efficiency, right? But also we don't want too few partitions. So a partition as a whole is being sent to a worker. So I have 5 workers, but if I only had 2 partitions, ideally, like rather only 2 workers here will be used and the other 3 are idling. So we want to choose number of partitions effectively. And how do you do that? A little bit of trial and error, I guess, but also these plots will help you. So if you see like the worker memory just skyrocketing, you know that you need more workers. And with more workers, you want to like correlate and have more partitions. Okay. Also, this depends a little bit on the type of task as well, right? Some tasks are a lot more parallelizable, like we had an example of mean versus median. So a mean is like a lot more parallelizable than a median. So if all of your computations have a very non-shuffling, like rather minimal shuffling workflow, like that's the kind of workflows you have, you can get away with more partitions there as well. So there's a little bit of nuance, but it's another like thing you want to consider when you do distributed compute. It depends on the resources. I know not okay. So the question here is, what is the optimal number of partitions or the optimal partition size? As Kim said, it depends on the number of like your workers, your compute. There's there are a lot of cool blog posts about this. So yeah. All right. So let's move on. let's move on to, oh yeah, so the two change partitions, you can use the repartition method. Okay, so we have a couple of exercises for y'all. I will run the solutions, and you don't have to. You can take a pass at this yourself as well. So now we are going to, actually, you know what? We have 50 minutes. This is quite similar to what we had earlier. We're doing a repartition and then another compute. So I will actually skip over this, but I'll let y'all take a look, okay? Okay, this is the final piece we're discussing about distributed compute. And this is actually very task specific. This is not broadly applicable to distributed compute from what I can tell, which is the meta keyword. So as we discussed earlier, every time you set up a computation, like before you actually do the dot compute, right? When you create the task graph, Dask is making a educated guess about the kind of output at each stage. So when I do a group by, then I do a a count or group by and apply something, applying a function. Dask is making a guess about what the output of a group by will look like, chained with the output of a compute. Like a count is going to give me a number at the end, so it's going to make a guess and think and like design the task graph that way. But sometimes when you don't use when this chain becomes too long, or when you don't use said or like functions that task understands, like for example this question where we have a custom like lambda function which task does not understand, what should it do? And like that's where it will throw a warning saying specify the meta keyword. So meta is how you can tell Dask what kind of output to expect at the end of this compute. So here, this is most relevant usually when we use apply, because that's where a lot of custom functions come in. Okay, so to use it, what you can do is create a sample like empty data frame, because at the end of this, I expect to get one, a Panda series. So the output is going to be a series, right? So, and pass that to Meta. At the end of this, Task knows this is the kind of output I should expect and can run this computation in a more like reliable manner. So if I do this, I shouldn't have any, oh, I didn't import pandas, never mind. I shouldn't have any major errors, but that should be helpful. Okay, any questions here? All good? All right. So usually, even without specifying it, like in some cases, Dask can makes the right guess, but it's usually just best practice to always specify. So just for reliability, right? Okay, so with that, like we've come to the end of the task section of this, like just generally analyzing your data sets in parallel. After this, we'll move on to visualization. All right. Here, actually, I did comment out the cluster and client shutdown section for everybody. So just that you also get a chance to continue with the same cluster. Because like this is one of the most time-consuming bits and work in the cloud. I messed up my, oops. Give me a second while I get this sorted. Yeah, we don't need the graph anymore. Let's just use the memory plot. Okay, yeah. So yeah, most of you shouldn't have shut down your clusters after the previous notebook, and can just continue using that if you reconnect to the cluster section in the third notebook. Just maybe give me a thumbs up if everyone's done with the previous one, because this is the next section and we're kind of shifting gears a lot. Okay. Let's do the same. I'll also connect to my cluster here and get a client. All right. So now for the visualization section, here's where we're actually going to use hrplot. We will work with only like a subset of our data set, because even with this cluster, visualizing things takes up a lot of compute behind the scenes. Okay, we have a few different comments actually. Yeah, that's kind of why. Let me wait for a couple more minutes, right? Like while folks catch up. I'd rather not. Like, I don't want y'all to do multitasking. So yeah, let's complete and like shift gears to visualizing. So now all of the distribution is going to happen behind the scenes, right? If you actually want to, you can just close all of the plots. I'll just leave them on. Let's just leave one plot on actually. We don't need any of these anymore. This one just to make sure like this is an easier way to see that more workers are coming on, like, or if some of my workers died, I'll know immediately. But there are other plots that give you this information as well. I know. Yeah, such great bokeh stuff. Okay. All right. I guess I will ask folks, even if you haven't already, let's move on to the third notebook. We have about 40 minutes. So let's cover this, and that way we'll have some time for questions at the end. I think I'm going to have a lot of questions. Okay. So visualization and big data visualization in specific. We have a lot of visualization tools in the PyData ecosystem, right? And all of them have their own special purposes. For this tutorial, and especially, I guess our team, right, is a lot more familiar with the HoloViz toolkit. So HoloViz is a set of tools which includes hrplot, but also panel, HoloViews, data shader, like a bunch of interactive visualization tools that are like really powerful, built for specific use cases. So hrplot, what we're using today, is you can think of it as a interactive replacement for the .plot API that we have in Pandas. This is a very, in our opinion, a very like friendly way to get into the interactive visualization landscape. And like it also just provides a lot of nice default options for us. That's why we're using hrplot. But if you're really curious, and honestly, this is actually quite fun, I would fully encourage you to go through and check out like HoloViews, Shader, Panel separately, because they're all really powerful and awesome. Okay. So as this like visualization, this diagram suggests, hrplot is like a wraparound, or like provides the same interface as .plot in Pandas, and it works with a lot of different data types. So you can actually use hrplot with Pandas directly, but because we've been using Dask so far and Dask data frame, it also plugs in just equally well with Dask, but also all of these other options like X-ray. Just gonna drink some water. And behind the scenes, this uses HoloViews. HoloViews is like directly a layer over bokeh. Like bokeh is an interactive visualization library, a more fundamental library that is built like for the web, and HoloViews is like a layer on top. htplot uses HoloViews and data shader, which we actually look at data shader again at the very end here. But data shader is for actually really big data computes in a visualization, but we'll get to data shader in a bit. And HoloViews actually works with Matplotlib and Plotly as well if you want to use it separately. Okay, but today we're using htplot. Okay, so let's go ahead and just use a subset of our full data set. So using only a certain number of columns and filtering the year, we're only going to be using 2021 onwards. Folks are not familiar with Parquet. This is a feature of Parquet. It's a columnar data format. So that data is stored in a columnar format. So we can do things like filtering. So we only read certain parts of our full data set, and we can control that programmatically. Nishan, can we use the HoloVis framework to view data frames? Yes, actually, we're going to do that just now, right now. Right. So out of first off, the flights is where we're going to store our data set. Like we've only used data from 2021, right? And we are creating another subset where we are just narrowing this down to a few carriers. This is just to make sure we get the plots quickly. Okay. So even with this filtering, we have quite a few million rows to work with. So first off, we did this so that we can persist this. And as you know, we persist a small amount of data that we actually need for computation. And persisting will let us just access these pretty quickly. And the compute will be behind the scenes handled in a way that is efficient with data locality. Okay. So to use htplot with task, we will import htplot.task and we'll enable an extension. So we're going to be using bokeh. Do that. So make sure this cell is executed just because of how Jupyter Lab and htplot and bokeh all work together. Oh, thanks, Kim. You meant how to see the data frame itself. Yes, Kim has shared tabulator. Yeah, so if you want to see actually the table itself, like the data in a more interactive manner, yes, you can do that with HoloVis, and tabulator is the one. I thought you meant plotting it interactively. Sorry. Okay, so let's do a quick plot. So we will, this is the same compute we did in the previous notebook where we plotted departure delay per day, right? And let's do it. So instead of dot plot in pandas, we do dot htplot, and because we are using htplot's task in htplot for task data frames, it will do the compute behind the scenes for us in the right way for this. Okay, let this compute. There we go. That was a lot quicker. And we'll take a moment to actually go through this for folks who are not familiar with bokeh plot. So by default, you have certain tools, right? First off, these are htplot has given us some defaults on top of bokeh plot. So we have a hover tooltip. You can hover on the plot and see details about that data point. You can zoom in if you want with the box zoom, right? There is wheel zoom. Just go ahead and explore these because you'll end up using them for the rest of this notebook. You can save this plot directly with save, and just to reset this to the base version, you can click on reset. Okay, so this is an exercise for you to write up another compute for visualizing the weekly distribution. Do a mean on any variable in that data set. You can see the list of columns here and do a .htplot. Let's see what we have. We did arrival delay, again, pretty similar to our previous one. And an additional thing you notice here is dot scatter. So this is h3 plot syntax. So dot scatter is telling h3 plot. So by default, we had a line plot here. It's telling h3 plot to use a scatter plot instead. So we have scatter. And you can look at the h3 plot gallery link here. We have a lot of different plot options. So depending on how you want to visualize things and like your actual computation, you can choose different plots here. Okay. So that was just a basic plot, right? But to make more of interactivity, we can also have widgets. What is a widget? Let me actually press compute. So a widget is any additional thing you have in as a part of your overall visualization that adds more interactivity. It can be a drop down to select certain things. It can be like radio buttons. It can be text input, like you want to change what is displayed in the title, for example. So like these additional elements of your overall visualizations are what we call widgets, at least in the space. And h3 plot kind of uses, like has h3 plot, because it's a wrapper around a lot of other things, it creates the right widgets for your compute visualization. So here we did a here we plotted a histogram, and we did group by OP carrier, and like we've only selected 4, right? So all of those are available as a dropdown for us here. And this is handled by h3 plot. All we had to do was call h3 plot. And this remains interactive. And the cool thing it does actually for this one, let me open up the task stream. Because if I change the carrier, it's going to do a compute behind the scenes and give you the new result. Ooh, in a very large time series, it will change the sampling when it zooms in and out. So that's where data shader comes in actually. By default, it won't. Like if you use all of the h3 plot directly, the plot itself is not going to trigger any compute behind the scenes, right? Like if I do a zoom here, you'll see nothing is happening on the task plots. But when we go to data shader, that's kind of what data shader was built to do, was to visualize these really, really large volumes of data and be able to sample these in a more interactive way. So like there, when we do a zoom, it'll trigger a compute and like give you a more granular view of things. Okay, so so far all here. So quick widgets is basically h3 plot handling certain widgets for you. Okay. The next cool thing about h3 plot is the ability to quickly compose plots. So let us set up a couple of computations. We are going to group by day of week and the carrier and plot the departure delay and compute the minimum, mean, and maximum departure delays here together. And let's persist this data, this plotted data. Sorry, this computed data. Next, we are creating 2 different plots. First is an area plot. Right here, we are plotting minimum and maximum values as an area. And second is a scatter plot of the mean departure delay. Okay, so we have a min-max plot and we have a mean plot. Let's compute this. That's the mean plot. And sorry, the min-max plot and another mean. So composing is just putting these side by side together in a single panel. So if we actually reduce this, you can see these 2 are positioned side by side and share interaction elements. And overlay is plotting these on top of each other. So that's where you can use the star shorthand. For composing, we use the plus shorthand. So these can be really powerful. This is actually kind of tricky, or like you will need a lot more code to like put this in we call this, I think, a layout, right? Like your especially the top one, this is like a row layout. You're positioning plots in the layout, but htplot makes it really easy to put these together. So now, yeah, these two are combined and can be used together. All right. We have a question. So for a bouquet plot output cell, if I mark the cell type as a slide type, in React.js, I think that should work, because once the plot is available, it's just yeah, I haven't tried that. I think it should work though. Let us know if you like have it handy right now, or we can try it at the very end if you remind us. Okay, so those were like the highlights of htplot. So we've like picked items to discuss, like, because for the most part the power comes from like actually following the .plot API, right, of pandas. So we don't want to keep doing that compute over and over again. So these are the other cool things you can do with htplot. But next, let's move on to Explorer. So this is almost an aside, but like not quite. This is going to be most helpful actually when you work with pandas data frames. So that's kind of why we've actually done a compute, and a compute on a DAS data frame is going to give you a pandas data frame. Okay, so let's do that. And Explorer, I actually don't want to explain it. I want us to load up if we can. While this happens, feel free to like go through the previous one. There's a lot of interaction to play around with in the meantime. Explorer is like a graphical tool. It's very hard to explain without seeing, honestly. For you to just make sense of and like see what are the interesting ways you can, interesting things you can infer from your data set. So you call Explorer on your entire data set, right? And it gives you this dashboard-like view where you can select the type of plot, X and Y axes, any, if you want to group it by something, what kind of operations you want, plot style, and let's change a few things. Shall we, like, let's change this to scatter. Oh no, sorry. Let's do the scatter. Not everything will work because, of course, be very careful about what we are plotting. X can be here. Y-axis, let's do, okay, no, let's do something we've actually done. Departure delay. That's what we've been plotting so far. I know a lot of folks might already be bored of it. Let's do it by OP carrier. That's what we did previously as well. And you want to do something else? I don't think so. Anyway, so we have a plot, right? And we can get the code to create this plot with htplot. So it's like an interactive way for you to explore, as the name suggests, your data set. It is just fun, this thing that htplot provides, which can be actually quite useful. But again, use this with a pandas data frame. Like this can get, if you use it with like a full data set, it can be really slow and tricky to work with. So this is something you want to use for exploration alone. Yeah. Okay. To let y'all play with that some more, there is a your turn an exercise here where you can use the Explorer to plot site cancellations per day. So you can like generate the code and then use that code to actually get the plot again. And to save your Explorer generated plot, it also provides a .save function. So you can use that. Yeah, that. So Explorer will crash if you try to do too much at once. Because it's actually, that's kind of why we computed and only use the data frame that fits in memory here. I won't go through that. I'll let y'all take care of it. Next, so all of our basic plotting is done, right? Now let's move on to some geographic plots. We'll get back to we have about 25 minutes left, so I'll just try to like complete this, wrap it up, and then go through all the questions at the end together. So geographic plots. We don't have any geo data in our data set directly. So what we've done is we've downloaded a new one, a new data set, which has the latitude, longitude values for US airports. So that's available on GitHub there. So let's just download that and merge it with our existing flights data. Okay, not the flight data set, but like creating an airport delays data frame, which does a group by departure delay based on airports. So we're gonna see on a graph where these lie. Like sorry, on a map where these lie. Sorry. Okay. Let's persist the airport delays because now that's the data frame we'll end up using. Okay, so now airport delay has our geographic data, so lat-long values for US airports, and these are we are plotting the mean departure delay for each origin airport. Okay, just putting this all together. Now let's look at what our complete, like what the data set we're working with is. That's that. And now we will use htplot.points. So points is another like glyph. So we have scatter, like circular small glyphs we have. So points does that. And we're going to use geo equals true to use geographic data. And behind the scenes, this uses GeoViews, which is another HoloViz ecosystem toolkit, which is designed for more geographic first, or like geographic plotting. Okay. I will go ahead and execute this. Oh, what happened here? I think it's just naming that I might have messed up. Latitude and longitude weren't found. It's the, okay, I'm doing index. We have X and Y as separate merges. That's okay. Let's do longitude X and latitude X. Let's plot X value. So when I did a merge, this is the task data frame merge, right? Yeah, so we didn't get into this a little too much, but merging, there are a lot of ways you can do merges, and merging in task data frame, you can read about it in the documentation, and the way task handles merges. That's kind of why we got into this. Okay, yeah, there you go. That worked. Now I want to zoom in a little bit. And I should also be able to hover and see what the departure delay was. And we have a color bar here to indicate and give us a more holistic view of like if you want to see something in particular. Any questions here? All good? Okay. So to be clear, like these last two sections, we are not going to go into too much details. Like this is just to show because htplot is a part of the HoloViz ecosystem, like there is a lot of powerful tools we can leverage through htplot, but also use those directly. Okay, lastly, data shader. So I will actually just execute these pretty quickly. We discussed this a little bit earlier, right? So so far, whenever we've done or looked at data, the plot itself is is client side. Like, there's no extra compute happening to give us anything special. Like when we zoom in, it's literally just zooming in the plot itself. But when we actually plot, like, so these points are fine, but when we have too many, this is going to get super congested, and all you will see is like a gradient of blue. So there, when you zoom in, you want more granular information, but we don't, that information isn't preserved, right? Because they are also working distributedly, and like to see that information, you will need like all of your data to be computed together in a place, which we can't do. So what Datashader lets you do is it leverages like tasks behind the scenes, but when you zoom in, like you can then trigger compute to see a more granular view of certain parts here. So we will see that in just a bit. Kim, do you want to add something in this section? I know you've worked a lot more with visualizations, especially
I,
with these tools.
I wasn't listening, so I don't know exactly what you said.
No, I mean, I was just asking, like, do you want to share something about Datashader and GeoViews?
Well, Datashader is really awesome because you can plot so much here in the browser. So what it's doing is it's aggregating the data in the back end. So on the Python side of things, it's running the aggregation so that what's coming to our visualization is a downsampled data set. So we can downsample in a lot of different ways, but we're not losing the knowledge. So we can see the darker colors in this plot here indicate that we have more data points down there near the 0, right? But we don't have to actually see every individual point because Datashader is kind of handling that for us in the background. And then the beauty of HV plot is that all we had to do was throw a data shade equals true, and it's doing all this for us in the background without us having to specify anything, you know?
Yep. Like even when we do this locally, like the browser is going to crash if you try to visualize like such a large data set.
Yes.
Like forget like local machine, right? So yeah, this became a little more clearer because once I zoomed in, it can only trigger compute to show us that. But when you look at the overall view, everything is super downsampled, as Kim suggested. So yeah, I think with that, we've come to the end of our tutorial. There are a few more sections if you would like to take a look. Just a few options that you can use with Datashader. We won't go into these super in detail, but yeah. Okay. Any other questions? Like, okay, now's your time to ask all the questions actually. So I will like add this caveat, like we try to give like a very condensed view of, you know, what these tools, especially the power of these tools, but also generally how to think about things in big data world. So to use these in your day-to-day, you'll have to go in and refer to the documentation and understand the nuances of these tools. Don't forget to shut down your clusters. Should have said that before I said the tutorial is over at the end to make sure, yeah, all the resources are actually shut down gracefully. When you do that, like your plot should disappear. You shouldn't have anything available here. So, do folks have questions, general questions about what we discussed, about the platform, about anything? What's your recommended strategy to committing these interactive notebooks to version control? Other than just removing the interactive parts, is there a middle ground? I don't think you can currently commit, at least, okay, I'll add this. I'm only familiar with bouquet-based plots. I don't know about Plotly or Matplotlib's interactive elements, but with bouquet, you cannot currently commit these to, like, an HTML version will be saved, right? Like at the end of the day, even the interactions are handled through HTML. I think you're going to be losing a little bit you will have to recompute to get like the actual accurate value. For basic plots, I think if it's just like JavaScript side, like it should be preserved. Yeah, if you can version control your HTML, you should be able to do this. But like the full complete interaction, especially with the big data task attached things, even though you can preserve a certain state of the plot, the complete interactivity, like with the drop downs, for instance, those will not work because they need to be computed in real time. Does that make sense? Yeah, that as been suggested. Yeah. Uh, yeah. Generally, you shouldn't be saving your outputs. Okay, if we export as HTML, will we lose the zoom interactive? I lost the question. Yeah, if we export the notebook as HTML, will we lose the zoom interactivity with data shader? You can zoom in like the downsample data, right? Not really the, like, as you saw there, like once we zoomed in to a data shader generated plot, it was triggering compute to give you a more granular, like detail oriented view. You're going to lose that if you commit it. That, yeah, as Kim suggested, if it's going to do a dot compute behind the scenes, it won't be static anymore. Any other questions? Oh, thank you, Sabrina. That's very kind of you. It's been extremely informal and casual, to be honest. So yeah, I really appreciate that. Thank you. Uh, any other questions? I think yes. Is there a way to make matplotlib graphs interactive? There are limited yet useful interactive elements in matplotlib, but I don't know them personally. Yeah, you can look it up on the documentation. Using HoloViz. Uh, I know you can generate. So HoloViz is like the set of tools, right? Like HoloViz is the entire ecosystem. HVplot can generate certain matplotlib plots, but like matplotlib itself has like limited interactivity. So I think HVplot just does what it can. I haven't tried it myself, so yeah, I can't be super sure. Any other questions? I do want to give a huge shout out to like the developers, maintainers, like the communities around the Ask HTTP but also like overall the PyData ecosystem, right? Like the Ask HTTP won't work if like NumPy and Pandas don't exist, and if we can't use Jupyter Hub and Jupyter Lab. So all of this is coming from like the PyData ecosystem. So yeah, all of these tools are just awesome. So yeah, want to acknowledge that. How htplot and HoloViz work. I think the very first diagram in this notebook, right, has a fairly, yeah, this is like an accurate view of, and HoloViz is a set of tools. In this diagram, htplot, HoloViz, and DataShader are up, sorry, htplot, HoloViews, memes, and words are hard. These three are a part of the HoloViz ecosystem. And if you go to holoviz.org, you can see the actual complete set of tools that are part of the HoloViz toolkit. And the interactions are, honestly, I don't think I can just explain it. We'll need a visualization to show how these relate to each other. But they're all like interconnected.